Good morning, guys. Okay, so we're going to jump into the last two concepts in chapter 8. Okay, my instructions in the classwork section of Google Classroom gave you a very brief sort of introduction. But let's back up a little bit and talk about the concepts involved. So these can be found in the last two sections of chapter 8. I believe it's 8-9 and 8-10. But go ahead and check your book if you want to kind of follow along in those sections. So we're talking about direct and inverse variation. So we got direct and inverse variation, okay? So first of all, let's just talk about the basic idea here, all right? Variation means change of some kind, okay? So with direct variation, what that means is if we have two variables, if one variable goes up, the other must go up as well. Direct variation. As one rises, the other must follow as well, okay? Inverse is the opposite of that. So here's inverse. In the inverse example, again, if we're talking about two variables, if one value rises, the other goes down. That is inverse movement. As one goes up, the other must go down. All right, so just in terms of the vocabulary involved, let's be clear on that. Direct variation means as one variable rises, so does the other, okay? And these are both functional relationships, which means input-output. So as the value of the input increases, the value of the output will increase as well. That is for direct, all right? For inverse, as your input value is increased, the output will decrease. All right, so direct, inverse. Those are kind of the visual movements you can associate with those words. Okay, so let's talk a little more about direct here. Okay, so one example of a relationship that involves direct variation would be something like driving in a car. Okay, the speed that you are driving in your car, if that stays constant, so look at the example here. 10 miles an hour, okay? We'll talk about the constant part in a moment, but let me give you the example first. If you're driving 10 miles an hour in your car, then if you drive for 5 hours, you will travel 50 miles, right? 5 hours at that speed will take you 50 miles. Should be pretty clear. If you keep that same speed, but now you drive 10 hours, what's going to happen with the distance? It's going to go up. So if you drive for 10 hours at 10 miles an hour, you'll go 100 miles. So look, our input of 5 hours was increased to 10, and what happened with the output? So it went from 50 to 100. So as the input went up, so did the output. Direct variation, okay? Look at the inverse example now for a second, okay? Let's say that we know, I'm calling this job hours. Let's say we know it takes 40 hours of labor to complete a job. Well, if we start with 4 workers, they're each going to have to do a total of 10 hours to achieve that total that we understand to be the final conclusion of our situation. What happens if we increase the number of workers from 4 to 10? Well, if we increase the number of workers, the hours that each worker is going to have to complete goes down from 10 to 4. So that is an inverse relationship, okay? As the number of workers is increased, the number of hours each of those workers has to complete goes down, okay? And again, now in both these examples, there's what's called a constant. Here, we're deciding to hold the speed constant, okay? Over here, we're deciding to say that this job, which takes 40 hours, that's the constant. Now, when we get to actually solving the problems in the book, you're not going to have to worry too much about that information at this point, but I just want you to be familiar with that terminology. So if we were going to write down a direct variation problem in sort of its formulaic presentation, it would be right here. This variable, it's not a functional notation, this is a variable. So k is the unchanging part of the problem. X is one variable, y is the other. So the input and the output. So again, to take this and translate it into our example, in this problem, the constant is the speed. So if you're only going to travel 10 miles an hour throughout the whole problem, that needs to hold steady at 10 miles per hour. That allows us to set up the situation where if we drive for 5 hours, we go 50 miles. If we increase to 10 hours, we'll go 100 miles. That's how we get that direct variation. As this goes up, so does this. They both move up together, okay? On the inverse side of things, it looks a little bit different, right? Here we had k times x will equal y, that's the constant. Here we have x times y equals k, all right? So we're going to be multiplying these two variables and getting the same result, okay? Now, we can just do a couple things in our head and show that this makes sense, right? Let's take the number 12 for a second. 1 times 12 would be 12, right? If we increase x to 2, what does y have to be to get to 12? Well, it's going to be 2 times 6 equals 12. If we increase x to 3, what must y be? 3 times 4 equals 12. So the 12 is constant. That stays the same the whole time. But the relationship here is inverse, right? If the x is 1, the y has to be 12 to get to 1 times 12 is 12. If the x is 2, the y value has to go to 6. 2 times 6 is 12. If the x value goes to 3, the y value goes to 4. 3 times 4 is 12. It's that constant that determines that if the x goes down, the y must go up. All right, so again, inverse relationship, okay? All right, so let's take a little break now, and then we'll come back to some of the problems, focusing today on direct variation, okay? Okay, guys, let's start looking at some problems now. So open your books to page 395. We'll do a couple of the problems assigned for homework. Now, these are all going to utilize direct variation, okay? So let me see if I can give you sort of some good basic practical steps to solve these problems. So first of all, I want you to notice something. Let me grab my book. Just look at the wording for a moment for numbers, let's say 1 through 6. Look at number 1 there. You'll see the phrase directly proportional. Number 2 doesn't use the same phrase, but look at number 3. We see in the first line there, it says that the amount of money a magazine pays for an article varies directly. All right. Number 4, the speed varies directly. Number 5, directly proportional. Number 6, if the force varies directly. So in other words, the problem will tell you if the relationship is direct or inverse. And certainly on our future test, I'll be sure to include that key word, okay? So first of all, look for that word direct, either directly varies or is directly proportional. Direct, that will indicate it's a direct variation problem, and then that'll determine how we set it up, okay? All right, so look at number 1. An employee's wages are directly proportional to the time worked. So let's just stop and analyze that situation. That makes sense, right? What they're saying is the amount of money that an employee makes is based on the number of hours that he or she works. So if you work more hours, you get more money, right? Direct variation. As one thing goes up, the other goes up as well. All right? So here's the information now. If an employee earns $100 for 5 hours of work, how much will the employee earn for 18 hours? Now, you could take those first two numbers and get a rate, right? Dollars per hour that the guy is getting paid, and then apply it to an 18-hour situation. That's fine. But I want to show you how to set this up because not every direct variation problem will be so intuitive. So let's look at the board for a moment. First of all, it's our old friend, the subscript, right? X sub 1 over y sub 1 equals x sub 2 over y sub 2. Now we use these subscripts with the slope formula, but it's not what we're doing here, okay? What we're doing is we're taking a situation where there are two different x's in question, In this case, the x's are two different hour totals. So look at number one again. If an employee earns $100 for 5 hours, how much will the employee earn for 18 hours? All right, so notice that there are three things mentioned there. There's 5 hours, there's 18 hours, and there's $100. 1, 2, 3. Notice how many kind of variable spaces we have in our setup. 1, 2, 3, 4. That's going to be a constant pattern in these problems. The problem will give you 3 pieces of information, and a fourth is our unknown. That's what we'll be solving for. Okay? The thing to remember is when you're filling these 3 things into the variable spaces, you need to match them up properly. So for instance, I'm going to put my hours on top. So I'm going to go 5 hours yields $100, okay? And that's equal to 18 hours yields some other amount of money. All right, so now this is our variable, okay? Now I've mentioned cross multiplication before, and I'm sure many of you have seen it before. Let me get this in prior classes. But as a reminder, here's how it works. If we have 2 fractions equal to each other, then we can cross multiply. And it's a nice quick way to get rid of the fractional situation in an equation. So here's what we do. You multiply across from top to bottom that way and top to bottom that way. Okay? So 18 times 100 is 1,800. 5 times x is 5x. Now we have a pretty simple linear equation with no more fractions involved. We divide each side by 5 to isolate the variable. 5's cancel, there's our x, and we're going to get x is equal to 360. So what are we actually answering here? It's the amount of money the guy makes if he works for 18 hours, and that's going to be $360, okay? So again, you've got, before we plug anything in, you've got x sub 1 and y sub 1. So in this case, 5 hours, $100. Whatever other piece of information we get, in this case it's 18 hours, make sure it's across from the same type of thing. So if I put 5 hours here, 18 hours has to go here. You can't put hours here and then hours down here. They have to kind of line up. So 5 hours, $100. 18 hours, unknown number of bucks, okay? That yields the problem. We can cross multiply. The steps are right here, okay? Let's take a look at number 2. Okay, page 395, number 2. Let's read it first. A certain car uses 15 gallons of gasoline in 3 hours. If the rate of gasoline consumption is constant, how much gasoline will the car use on a 35-hour trip? Okay, so there are 3 things, right? We've got 3 hours, 15 gallons, and 35 hours. So 3 things. I'm just going to write them in kind of any order right here. We got 3 hours, 15 gallons, and then the third thing was, where is it? 35 hours, okay? I should actually label 35 hours, 3 hours, and 15 gallons. I'll just put that. Okay, so 1, 2, 3 things, but our setup has 4 spaces. All right, so again, we're going to plug in 3 things, excuse me, and then the 4th thing will be our missing variable. Okay, so let's do that, remembering that we have to make sure that similar kinds of things are on the same level of the fraction. So I'm going to go with 3 hours. I'm going to put that in the x sub 1 spot. So there's 3. For the moment, I'll leave the descriptors off. So 3 hours. And what was paired with 3 hours, right? It wasn't 30, it was 15 gallons. So in 3 hours, 15 gallons are used. All right, so there's the relationship. In 3 hours, 15 gallons are used. That's going to be equal to, all right, so now we have another fraction. So we found a place for 3 hours. we found a place for 15 gallons. We got to put the 35 hours somewhere. And we've got two different possible spots. Which one do we use? Somebody sing the Jeopardy theme. All right. If this total here refers to hours, then if the remaining piece of information is itself a number of hours, it has to be right across. So right here. So from 3 hours to 35 will bring us from 15 gallons to our unknown. Okay? So again, notice kind of the pattern. If we put hours on top on this side, we must put hours on top on this side. Similarly, if we put the gallons on the bottom on the left, that's what we'll be solving for on the right, the number of gallons in this new situation. So we have two fractions. They are equal to each other. We can therefore use cross multiplication. So 3 times x gives us 3x. 35 times 15. Let's do a little bit of board work. 5 times 5, 25. 5 times 3 is 15, plus 2 is 17. Add our 0. 1 times 5 is 5. 1 times 3 is 3. And we get 525. So I'm going to move this down a little bit. 525 will equal 3x. So we've removed the fractional situation, okay? We now simply have second to last stage here where we divide each side by 3. That isolates x all by itself. We get 525 divided by 3. And our answer, let me look at my work here, is going to be x is equal to 175. Okay? And again, what is this referring to? It's 175 gallons that will be burned if we drive for 35 hours. Okay? So, those are examples for numbers 1 and 2 on page 395. Do your best with the other ones, and I'll be online to deal with any questions that come up as you work. Okay? All right, guys, good luck.